Hello, good morning, and welcome back to the Nexperia Power Live Automotive channel. We're here for our last live discussion topic today, and we're going to discuss how to minimize and control losses with GaN FETs. So the session will start with a short presentation, and then we will open the floor for questions. So please do ask questions. You can do so by using the speech bubble in the bottom right hand of your screen. All questions are anonymous, so please do feel free to take the opportunity to ask anything you want to either of our power experts. I'm delighted to welcome back Jim Honier and Dilda Chowdhury, both from our Power GaN division. And with that, I will hand over to Jim.
Well, thanks, Kelly. Yeah, I'm Jim Honey. I'm Director of Applications specifically for the GaN FET product line at Nexperia. And we'll take a few minutes to talk about switching losses with the GaN FETs and then open up to questions. So starting point is just recognizing that low switching loss is a characteristic and an expected advantage of GaN FETs. That's probably why you've tuned in. You expect to lower your switching losses with these high-speed wide bandgap devices. So we're going to talk about where the losses actually are so that you can estimate what they will be in your application, and then talk about how to take advantage of that. So a very simple starting point, a reminder of what you already know, that switching loss occurs when the drain current and the drain source voltage are non-zero simultaneously. That's when we have an overlap voltage of current and we dissipate power with these very simple waveforms. It's this triangular shape, and the red area under the power curve is the energy lost during this turn-on transition. And we'll be using this circuit on the right here, a simple synchronous boost half bridge, where the low side transistor Q1 is the active switch, high side transistor Q2 is the synchronous rectifier, and hard switching, continuous conduction mode. And so what that means is all of the switching loss is in Q1. Q2 will have conduction loss, but the switching loss is in Q1, so that'll be our focus. From this simple waveform, something that is evident is that if we can speed up the turn on and the turn off, we'll reduce the loss, right? Decrease that overlap. And that is definitely true, but there is a contributor to the loss, which is independent of turn-on speed, and that's energy stored on capacitance at the switching node. This energy will be dissipated at turn-on, no matter how fast we turn on or off. And I've indicated that in this equation at the bottom. It's just a simple summation of capacitive energy, 1/2 CV squared, and that's dissipated once per switching cycle. Okay, looking at a more realistic waveform, you can see that the drain current doesn't simply rise to the inductor current and stop. It has to go above, and that delta I is the current required to discharge these capacitances, right? It's unavoidable, and the area under that delta I curve should equal the total charge on the switching node. Now, the capacitances we're interested in, some will be external, but a major one is the charge on the output capacitance of Q2. So when we turn on Q1, we're discharging, or rather charging Q2. And so that's what we'll take a look at here. And that is a no load switching loss. In other words, whether we have a load current or not, we will charge up that capacitance of Q2 using Q1, and there will be loss associated with it. So here's the steps we use to identify that loss. We start by recognizing that the charge drawn from the high voltage supply, VDD, in this transition is going to be QoSS. That's the output charge, right? Think about Q2. It starts with zero charge because it has zero voltage. And at the end, its VDS is at VDD. Therefore, its output capacitance must hold a charge of QoSS. So the energy drawn from VDD is VDD times QoSS. And that is all dissipated in Q1 with the exception of the energy stored on the output capacitance of Q2. that's going to be EOSS. Right? So the total energy dissipated in Q1 during this turn-on transition is energy drawn from the supply minus energy stored on Q2. We can get EOSS from the data sheet. We provide a curve there, or at the specific voltage of 400 volts, you can use 1/2 CV squared using the energy-related output capacitance, COER, as the capacitance value, but that only works at the specific voltage of 400 volts. Likewise, for the total charge, QoSS, we provide a graph. You can get QoSS at the correct voltage, or at the specific voltage of 400 volts, use the time-related output capacitance from the data sheet. So as an example, taking the GaN 041, that's a typical 35 milliohm part. From the data sheet, QoSS is 150 nanocoulombs, EOSS is 18 microjoules, and we can calculate the turn-on energy to be 42 microjoules. So that's the minimum energy that we'll ever dissipate simply charging the output capacitance of Q2. Now, you note this last comment in the bottom right there, where we say in principle, QRR at the exact load current could be used in place of QoSS, right? The cascode GaN FET will have a small amount of charge in the body diode of the silicon MOSFET. In practice, that 30 volt low voltage MOSFET does not have a lot of charge in its body diode. And in fact, when we do the measurements to find typical values that we put on the data sheet, we don't measure an appreciable difference. And so we typically put the same number for both QRR and QoSS. And so for these calculations, I'm simply using QoSS. But the point is, QRR would also be applicable. Okay, turn off. When we turn off Q1, the current in the inductor will charge the output capacitance back up to VDD. The turnoff is essentially instantaneous. And so all of the energy that flows into Q1 in this turnoff is simply energy charging the output capacitance. So E off is actually EOSS, which for this device is 18 microjoules. Okay, now if we add in a load current, we do get a switching loss that does depend on the load current and is related to the finite turn-on time. Okay, this is crossover loss, overlap loss, loss associated with the fact that it does take a finite amount of time to do this transition. And so if you see the equation at the bottom there, we have a crossover loss dependent on the supply voltage, the load current, and the turn-on time, delta T, with a proportionality factor, alpha. Now, back in the straight line example that we used at the start, that alpha is simply 1/2, right? That's the area of a triangle. In a realistic case, it won't be exactly 1/2. And what we find useful is to simply get an effective turn-on time derived from testing. And with the gate drive components that we typically use and recommend, a number of 10 to 11 nanoseconds is usually a good estimate. And that is for the alpha delta T, right? Just that combined time factor. And in the next slide, give an example of how we use that. The next two terms in this EON, the first one is charging COSS. That's what we just studied in the previous slide. And then finally, any external capacitance on the switching node. If there's printed circuit board capacitance that will be discharged, any winding capacitance in the inductive element, and that's simply 1/2 CV squared energy dissipated when we do the turn on. Okay, combining those estimates for E on and E off, the chart on the left shows what that will look like versus load current. Okay, the minimum E on is the 42 microjoule number. The line has a slope of 4 microjoules per amp, which comes from the multiplication of 400 volts times 10 nanoseconds, 10 nanoseconds being the typical effective turn-on time that we mentioned. Okay, now we have done double pulse tests where we specifically measure E on and E off, and we very closely match these two curves. So these actually do represent reality. It is difficult with a very fast switch to get an accurate measurement of the switching energies from a double pulse test. Invariably add inductance and modify the waveforms. So we also rely on other methods of confirming the switching loss, one of which is using DC-DC converters. It's easy to get a very accurate measure of DC voltage and current in a simple boost or buck converter. And then doing that at various frequencies, you can actually get a good analysis of the switching loss. So here on the right, we're showing a simple half bridge using the parts that we've been looking at, boosting 240 to 400 volts at 100 kilohertz, and comparing the calculated with the actual switching loss, or the efficiency rather, at 100 kilohertz. And you can see it is a reasonably good match. So this gives us confidence that we have correctly identified the switching loss in these devices. And one final point, switching loss is primarily interesting below peak efficiency at the lighter load conditions. Final graph here is measured efficiency for a 4 kilowatt totem pole PFC running all the way out to 4 kilowatts. And as you expect, beyond peak efficiency, roughly mid-load, there's a drop in efficiency where conduction loss dominates. Okay, and here it's I squared R loss with an element of self-heating. So the higher the power, the higher the junction temperature due to self-heating, the higher the resistance. And so there's actually some curvature in the declining efficiency with power, but that's conduction loss, not switching loss. Okay, so that concludes the comments I had, and I'll be glad to take your questions and insights at this point.
Thank you very much, Jim. Just to remind you, if you've got a question to ask, you can do so by using the chat function at the bottom of your screen. We've already got quite a few questions in, so let's make a prompt start. Jim, are the drive stage losses now significantly different with GaN devices? Are they now comparable to switching and conduction losses?
The drive stage losses, was that the question, Kelly?
Yes.
Okay. Yeah, actually, the driving stage losses are relatively insignificant compared to switching and conduction losses. We drive these gates 0 to 10 volts, input charge on the order of 20 nanocoulombs perhaps, and there simply is not a very high power dissipation in the drive stage. So if that was the question, the gate drive, and to be honest, we largely neglect that in our analysis because we're so focused on the power stage losses, the losses associated with the 400 volt bus or the high voltage bus are much higher. Hundreds of milliwatts would be a typical number, I think, for the gate drive circuit.
Okay, thanks, Jim. The next question is, I am wondering if GaN FETs are presently being used at commercial level for EV power electronics, such as onboard charger, AC to DC converters, or is the market currently only using silicon and silicon carbide?
As far as this, I won't give you a definitive answer because I don't have that visibility into what's actually in the market around the world. I would say silicon is predominantly in use. Companies, as you know, automotive companies are slow to release product into final production. So whereas I think everyone in the world doing onboard chargers, DC-DC converters, is developing GaN designs, evaluating GaN designs, to varying degrees, targeting production for GaN designs. I don't know that anyone is in production today with GaN.
I can
Yeah, go ahead, Dilder.
Yeah, I can just help Jim on this one. As the GaN is a very early stage of adoption in the market. Currently, in the industrial space, the GaN is being adopted. So there are quite a few designs, Corsair, and in the power supplies that they have started using and bringing products to the market. I think at least there are about 5-6 different companies currently bringing the GaN-based power supplies in the market. And the automotive sector, as Jim highlighted, is they're slow to adopt. They need to go through quite a bit of qualification. And from that context, they're looking into the current industrial market adoption and their design evaluation ongoing, and they will be bringing their products in the market soon. The predominantly at the moment, as you have said, Kale, it's silicon and very small scale silicon carbide, because silicon carbide is also not adopted. Similar like GaN, the both wide bandgap materials, they are not as yet adopted in the automotive market as much in the onboard charger or the DC-DC stages, but it will be coming soon. We are at the inflection point of adoption, so we'll be seeing quite a bit of designs in next year or and the coming years.
Okay, thank you, Dilder. The next question is, how is the switching loss minimized compared to silicon MOSFETs, as there are 2 die cascaded inside?
Yeah, the key thing, the 2 dies, one silicon MOSFET, which is normally off, is a 30-volt MOSFET. So the charge associated with that is quite small compared to, say, a 650-volt silicon MOSFET. So very low charge associated with silicon MOSFET. The high voltage device is the GaN FET, which is normally on. And the key thing for keeping switching loss low is to achieve the desired on resistance with the minimum amount of charge, right? It's moving these charges around where you get loss, as we've been talking about. And so getting an on resistance with the absolute minimum charge is the key to having minimum loss. And that's where GaN gives an improvement over a 650-volt silicon MOSFET. We can get 33 milliohms with much less charge because, one, the mobility is so much higher. It's a high electron mobility transistor. And 2, the spacings are smaller because it's a wide bandgap device. So we can space the source drain gate much closer together without breaking anything. So we have less parasitic capacitance due to the area of the structure and much less charge simply based on the mobility. So in the critical high voltage device, we take advantage of the capability of the GaN material to have lower charge. And in that way, we have lower switching loss than you would get with a silicon device, a similarly rated silicon device. Now, one factor that plays very heavily into this is the recovery charge. And so if the topology is one where the MOSFET has to carry a freewheeling current and the body diode conducts, there the silicon MOSFET has tremendous amount of charge compared to a GaN FET. And consequently, circuit designers will avoid topologies that require a silicon MOSFET, a high voltage silicon MOSFET, to carry current in the body diode. And so to get a high efficiency, it's a more complicated topology, perhaps a dual boost kind of topology where the MOSFET is only a low side switch and is not called on to carry freewheeling current. So I think I've I've tried to address the question there, but the fact that there are two dyes is not critical.
Yeah, just to
Go
avoid
ahead.
confusion, Jim, the low voltage MOSFET is only the body diode QRR is very, very low. So we shouldn't confuse between the high voltage MOSFET, very huge QRR, versus the low voltage used in the gallium nitride cascode structure, where the QRR is very low and it recovers very fast, and it doesn't cause huge amount of losses in that sense. So it's quite simple.
Good point. Thank you, Dylan.
Okay, thank you both. And the next question is, you include VDD as the voltage factor in the load dependent loss factor, but can't that voltage be made lower if there is inductance in the power loop?
Indeed, that's an interesting question. Let me go back to the to these waveforms, and the question is, if you look at the blue line there, which is the trace of VDS, when the current is rising, the dIdt portion, there is a voltage drop on parasitic inductance, right? LdIdt. And what that means is the voltage on the MOSFET when this transition is happening has been lowered, right? So the VDD number that I'm using is an increasingly inaccurate approximation to the extent that the voltage drops due to parasitic inductance. And that's something you can think about is, okay, well, why don't we just add parasitic inductance and make that voltage drop bigger? And that will indeed lower the loss, no question. But it's like any kind of energy capture, soft switching approach, active clamp kind of thing, where you have to be very careful that it is helping at every stage of the switching process, right? Because what you're really saying is you're going to put energy into that parasitic inductance. When will it come back and in what way? So if you can be clever about making sure that that doesn't come back and hurt you at a later stage, then yeah, absolutely. You can you use a parasitic inductance to lower the drain source voltage at the moment of switching. I would say with our demonstrators, we specifically avoid that simply because parasitic inductance complicates stability. And with a high-speed transistor, keeping the switching stable is critical, right? We don't want to create oscillators. And for that reason, I would say our recommendation is avoid parasitic inductance and don't try to minimize switching loss by adding parasitic inductance. But in principle, it would do that.
Okay. Good. Thank you very much, Tim. The next question is, how would PCB layout affect switching losses?
The main impact of the PCB layout is, I will say, is adding inductance, which creates resonances that can then overshoot and ring. And when there's energy associated with these ringing oscillations, that is lost energy, right? It doesn't contribute to output power. So that would be the most immediate impact. Now, because you don't really want to have that ringing, you will do something to compensate for the PCB layout, adding maybe an RC snubber or slowing down the gate drive with a higher gate resistance than you actually need. And so you will indirectly, or let's say the PCB inductance indirectly increases switching loss by forcing you to compensate for it. That would be one answer. A second answer is if the PCB layout puts capacitance on the switching node, that becomes lost. You see here the equation at the bottom of this slide, that last term with the external capacitance, right? with a large copper area on the switching node, you can easily create tens, maybe 100 picofarads of capacitance that has to be charged and discharged every switching cycle. So that is another way that the board layout can affect switching loss simply by creating capacitance. Dilder, can you think of anything I've missed?
I know that's basically the PCB inductances increase that half Li square losses, and that's then start contributing to the losses as well, because the loop inductance you would like to have the minimum, right? And that's why.
Yep, absolutely.
Okay, thank you, Jim. And it is the last session of the morning, so we'll squeeze in one final quick question. Is there any loss in zero voltage switching?
Actually, no. That's easy. Go ahead.
on this one, I probably in a perfect condition, yes, but whether you'll be able to maintain over the whole load area is the biggest challenge, because the soon you have got any load transition little bit uneven, then you start causing that zero voltage switching into a non-sinusoidal form, and that's where some of the switching losses comes in. Jim, you might be able to explain. It's a non-ideal part of the zero voltage switching when it can introduce some of the losses, right?
Yes, that's accurate. You'll see specifications put on loss during zero voltage switching, like hysteresis loss, where you have a non-uniform charge and discharge cycle, and with superjunction MOSFETs in particular, people have discovered that you will create loss in going through that charge-discharge cycle, even though externally it looks like you're achieving zero voltage switching. The GaN FETs won't operate in that same manner. One loss that you might encounter in the literature would be if that silicon MOSFET in the cascode ever goes into an avalanche clamping mode, which it is conceivable the amount of energy related to that is not alarming, but we have actually optimized the two transistors in the cascode to avoid that situation. And so we will not anticipate seeing a loss during zero voltage switching due to that factor.
Mm-hmm.
Right.
Super, thank you. Thank you very much. So that brings us to the end of this particular live session. Thank you both to Jim and Dilder again, and to everybody who contributed with the questions that we received. If you take a look below the video screen, you will see links for further information, such as our GaN FET product data sheets, how you can request samples, or links through to our eShop where you can actually buy the latest GaN FETs. Also, if you want to talk to somebody about our GaN FET technology, you can use the chat function on this website and speak to one of our power experts live, or there's also a mechanism for you to send an email if you prefer to do that. So this concludes the live program on automotive for today. We continue our schedule later today over on our packages channel. We've got a packed schedule this afternoon with discussions on Nexperia's LFPAC family, the thermal performance of our CFP60 package, and also our latest surface mount package innovation for gallium nitride RCC pack. So you can take a look at that schedule over on the packages channel, and we look forward to welcoming you back later today. Thank you.